Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expertise in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. So, we have theory of computation as the subject of this matter we are having as far as these episodes are concerned. So, in the previous episodes we are studying the Turing machine and the various versions of the Turing machines, especially the Turing machines with finite control storage having the there is one or more number of locations for that is having symbols which can be stored and used for later stages of the recognition. Then another one we have seen, that is Turing machine with one tape but having multiple number of tracks, so that there is one track of the Turing machine can be used for holding the that is input symbols, but whereas the other tracks can be used for that is maybe checking of symbols or even storing, that is anything for copying information, like that we can make use. So, they are actually the different, that is varieties or the facilities provided for the designer of that is Turing machine for different problems. So, these features actually helps the programmer or the designer in terms of that is while designing the that is Turing machine, they will find it is easier for some specific problems, like the problem like when you are recognizing WC, W reverse, or even WC followed by W. So, where it is required to remember the symbol which you are recognizing from the first part of the string, which is to be remembered when you reach the second part of the string also, maybe the rightmost end or in the beginning of the second part of the string. So, storage is very important as far as that is this kind of language recognition is concerned. So, we will make use of the finite control storage for that. And another thing is that is how do you know whether a symbol has been already processed or not. So, having that is known that some symbol has been already recognized, then we will not consider once again the same symbol for recognition. So, one way of achieving that is the symbol can be completely deleted from the Turing machine tape. In that case, what will happen is we will be losing the symbol at the end of your recognition. The other way of handling that is those symbols can be replaced by some other symbols, saying that the symbol has been already processed, but it requires a lot of work in order to restore the input at the end of the recognition. The simplest idea is this: if you are interested in that is restoring the input even after recognition process, you go for one more track of the Turing machine on the tape, and that track can be used as the track for checking of symbols. Maybe that is what we have stored, what we have recognized, or what we have used, or what is not yet used. So, using that kind of Turing machine versions, we have seen that the WC, W reverse can be recognized, or even WC, W can also be recognized as far as the previous episodes are concerned. But another important thing which we have to remember as far as the varieties or the facilities of the Turing machine is whether they would increase the capability of the Turing machine in terms of the language recognition power or not. And we are very sure that the language recognition power will not change irrespective of whether it is going to be a storage on the finite control with one or more number of locations or multiple number of tracks. So, they will never increase the capability of the Turing machine in terms of language recognition power. The only class of language that any Turing machine can recognize is going to be the recursively enumerable language. Whether it is going to be a single track Turing machine or multiple track Turing machine or Turing machines with more number of storage on the finite control, they all have the same power in terms of the language recognition, that is called recursively enumerable language. In terms of the design, we will find some easy, there is advantage with respect to the different varieties of the Turing machine. As far as this episode is concerned, we are having that is the multi-tape Turing machine, and another one is called that is non-deterministic Turing machine. So, we have seen in the previous episode that the tape, but we are having more number of tracks. So, the main difference in between the multiple track Turing machine and the multi-tape Turing machine is on how many heads we are having. So, or the how many finite controls that is we are having. So, as far as the multi-track Turing machine is concerned, whether we have one track or there is n number of tracks, there is always only one finite control or only one tape head which is capable of reading almost there is one there is vertical that is column or one column of symbols, they all will be on the same column. That is every symbol we are reading must be on the same column. So, but will be in different tracks. So, if I am having 5 track Turing machine, I can read 5 symbols at a time, but all of them should be available on the same column. It is because of there is exactly one head which is doing the reading process. But whereas in the case of the multiple track Turing, so multiple tape Turing machine, so if you are having n number of tapes on the Turing machine, there will be n different heads which are completely independent of each other will be available for us. So, I can read the ith symbol from the first tape, and whereas the jth one from the second tape and kth one from the third tape or anything from that is different tape. So, that is the main reason there is main difference in between multi-track Turing machine and multiple tape Turing machine. So, in terms of the complexity, your multi-tape Turing machine is more complex than the multi-track Turing machine. It is only because of we find more number of heads are available. So, for even a single move as far as the entire Turing machine functionality is concerned, we need to process all the tape heads, or we have to take that is all the finite controls into account, so that there is one move can be done after consulting all the tapes and the corresponding heads, what they are pointing and what is the symbol available on the particular tape, and whether the move is going to be a right move or left move. So, everything must be carried out in order to finalize one operation on a multi that is tape Turing machine. So, let us see that is how we are defining that multi-tape Turing machine here. So, we have there is finite number of tapes with exclusive heads for each tape. So, that is what earlier also I told, it is not like multi-track. Here we are having different tapes, and for each tape there will be an exclusive head available. So, the control or the finite control is completely independent of the other finite control in terms of whether it is going to be a right operation or read operation, or whether it is going to be a right move operation or a left move operation, or staying back on the same state. So, it is all completely independent of each other. And as far as the first that is tape is concerned, we will be having only the input. So, because input is always going to be a string, so mostly we will be storing the input on the first tape of the Turing machine, whereas the second and the remaining tapes of the Turing machine can be used for any job which is required for the processing of the input symbol. But in the initial stage is concerned, the complete that is tapes other than the very first one will be empty. There is only we will be having blanks as far as the remaining tapes are concerned. The first tape always is holding the input what is to be processed, whereas the remaining tapes are going to have completely there is blank. Since the remaining tapes are all completely blank, so the head position initially available on the remaining tapes is not going to be an issue. So, by definition of the Turing machine, the tape is always going to be infinite on both directions, it is not restricted. So, if since it is completely empty, you are free to move towards right any number of positions, and there is move towards left any number of positions. So, where we are starting is not going to be an issue. So, arbitrarily your head can be in any position as long as your tape is going to be an empty one. But that is not true in the case of the very first tape, because it holds the input which is to be processed. So, as far as the input tape is concerned, that is the tape 1 which holds the input is concerned, the finite control is supposed to point on the left end of the entire input. So, if W is a string which we are having which is to be processed, then the left end of the W is pointed by the finite control initially, whereas in the rest of the tapes the finite control may be available anywhere. So, your head of the first tape is at the left end of the input, and other tape heads can be in any arbitrary position because they are all completely blank. So, since all the tapes except the input tape are completely empty, the initial position of the heads are not going to be an that is issue. Also, that is the move of the Turing machine. So, it is completely depending upon the symbol scanned by each tape head. So, it is not going to be the first tape read and you can't take the immediate action for immediate that is operation for the that is next step. It is not like that. You read the first tape, read the second tape, and there is the nth tape. So, after reading all the tapes, you just process what is going to be the action, and even for that also we have to we have to process every tape available in the Turing machine. Once again the reverse process, when you start with first tape, second tape, etc. up to nth tape, you read the complete input and decide what is going to be the course of action based on the Turing machine, that is transition function. Then redo the operations, maybe the write or read, whatever it is, from the nth tape, n minus 1th tape and up to the first tape, do everything. So, that completes one, that is operation of the entire, that is Turing machine transition. So, what will happen in each, that is move, as far as the Turing machine is, it is going to enter into a new state, that is as usual, as far as since we are having multiple number of hits available on multiple number of tracks, multiple number of Turing machine tapes. So, every head can enter into a new state, and similarly that is if you are making change, or if you are processing all the heads, that is once the processing of all the heads have been done, it will tell you that we are going for a new state of the Turing machine, which is the multi-tape Turing machine. Multi-tape Turing machine has multiple number of tapes. In each tape there will be a move, so they will be changing the state of those moves, and altogether after completely processing all the tape heads, we will find that the new Turing machine, there is a Turing machine with a multi-tape, will enter into a new state, and on each tape the new symbol, you can write a new symbol, or we can even read a symbol, say if you want, or you can even simply leave that as it is without any modification of the tape content. Also, there is after reading or after writing the symbol or after leaving it as it is, the tape head is possible, it can move towards left or move towards right, or it can even be stationary also. That is, we can even keep the tape head in the same position. It is possible provided if you are having multiple number of tape heads, but whereas when you are having a single tape head, then if you keep these your position or the tape cell as the finite control stationary, then we will not be able to have any kind of move further. So, that is what, as far as the multi-tape Turing machine is concerned, the tape heads are allowed to move towards left or towards right or even stationary. But the very important thing here you have to remember is the heads are allowed to move in an independent fashion. So, the one head where it is going to be moving towards left or right, it has no significance in terms of the other head whether it is going to move towards left or right or even being stationary. That is what, the heads are always free to move in an independent manner. So, we will be able to process the symbols in an independent manner. So, now when you are looking at the capabilities of the Turing machine, so we have seen that one tape Turing machine, and then we have seen one tape Turing machine with the multiple number of tracks, and here it is the Turing machine with the multiple number of tapes. So, generally the language of any Turing machine is going to be the recursively enumerable language. So, that is going to be the language of the Turing machine in the standard form, that is with one Turing machine, there is one tape. But here we find that the Turing machine is having any number of can have any number of tapes, and all the tapes are having their own heads, they can move independent of the other heads. So, what will happen for the language of the Turing machine? Still it is going to be a recursively enumerable language. So, whether you go for one tape Turing machine or one tape Turing machine with multiple tracks or multiple tape Turing machine, the capability of the Turing machine is not going to be enhanced, because the language recognition power remains same. The class of language recognized by the Turing machine is only recursively enumerable language. So, if it is always going to be a recursively enumerable language, irrespective of whatever be the facilities introduced into the Turing machine, so there should be always a provision available for transforming a multi-tape Turing machine into a one tape Turing machine. If you can simulate the behavior of a multiple tape Turing machine with the help of a single tape Turing machine, then immediately we are able to prove that the Turing machine or the language recognition power of the multi-tape Turing machine is same as the language recognition power of your single tape Turing machine. So, to prove the language of your multi-tape Turing machine is going to be a recursively enumerable language, we have to prove that it is always possible to transform or simulate the multi-tape Turing machine in terms of the single tape Turing machine. then we can immediately declare that the language recognition power remains same. So, we shall see that proof after a short break. Welcome back. We are seeing the multi-tape Turing machine, and also I said that the multi-tape Turing machine can be simulated with the help of a single tape Turing machine. It is because of the language recognition power of multi-tape Turing machine remains the same as the language recognition power of the single tape Turing machine or one tape Turing machine. Let us see, that is how we are proving that the language recognition power is going to be same, or the language of multi-tape Turing machine is also going to be recursively enumerable, that is language. The simplest idea is, if you are having a Turing machine with k number of tapes, now you can go for a tape with that is 2 into k number of tracks. Actually what is given for us is a Turing machine with k number of tapes, and k number of tapes means we will be having k number of tape heads. So, all of them can move in an independent fashion, but whereas when you are going for simulating the multi-tape Turing machine using a single tape Turing machine, the tape which we are considering is supposed to have 2 into k number of tracks. So, what for we will use the 2 into k number of tracks is, actually in the given Turing machine we have k number of tapes. So, in the k number of tapes there will be some values available in the tape, that is tape contents, and all those k number of tape contents will be copied into k number of tracks available in the multi-track Turing machine which we are considering for the simulation. Then we also know that in the multi-tape Turing machine, for each tape there will be an independent head available. So, they are all capable of marking the current position of the tape in an independent fashion, but that facility is not there as far as the multi-track Turing machine is concerned. So, it is always possible to, that is, mark one particular column as the that is current input, that is part and current input tuple as far as multi-track Turing machine is concerned. When you simulate the behavior of a multi-tape Turing machine in terms of the multi-track Turing machine, how do you get the, there is feel of different heads available? So, different heads actually they are all exclusively used for pointing different positions on the tape. So, it is enough to know, that is, what is going to be the current position pointed by the head of the ith tape, what is going to be the current position pointed by the head of the jth tape. So, that can be easily obtained by having some marker symbol for each and every tape. That is, as far as the single tape Turing machine simulation is, or single tape Turing machine is concerned, with the k number of, that is 2k number of tracks, the k number of tracks are used for holding the contents of k number of tapes from the multi-tape Turing machine, and the remaining k number of tapes, sorry, tracks are used for holding some marker symbol, and they all will be denoting what is going to be the current position of the that is tape head as far as the equivalent multi-tape Turing machine is concerned. So, with this we will be able to find out, that is simulate the behavior of a multi-tape Turing machine using a single tape Turing machine. So, here is the description available, that is the language L is going to be the one accepted by a k tape Turing machine, the Turing machine we call it as M. Now, we are defining a one tape Turing machine, and the name of the Turing machine here we call it as N, with exactly one tape, but how many number of tracks we are having is 2 into k number of tracks. So, the k denotes the number of tapes available in the k tape, sorry, multi-tape Turing machine. Of the tracks, actually they are used for holding the tapes of that is M, and the other of hold single markers denoting the head positions of the corresponding k tapes. So, this is going to be a typical scenario of view of multi tape Turing machine when it is transformed into a that is single tape Turing machine with multiple number of tracks. Actually, it is going to be a 3-state that is Turing machine simulated in terms of a single tape Turing machine with the 6 number of tracks. So, the first tape content is A1, A2, A3 etc. up to A6, it is all available in the first track of the Turing machine. The second tape content, it is B1 to B6, it is available in the second third track of the Turing machine, and the third tape of the Turing machine contains C1 to C8, is now available in the 5th track of the Turing machine. If it is a multiple tape Turing machine, we have independent heads to point A2 is going to be the current symbol in tape 1 and B5 is the current symbol in tape 2 and C5 is going to be current symbol in tape 3. But since it is going to be a single track Turing machine, single tape Turing machine, exactly one head will be available. So, we should know some mechanism for remembering what is going to be the head position in the equivalent multi-tape Turing machine as far as this single tape Turing machine is concerned. So, that is what we use the alternate tracks for holding the X mark, saying that your finite control points to A2 as far as the tape 1 is concerned, and as far as tape 2 is concerned it is pointing B, and as far as the tape 3 is concerned it is pointing C5. So, that is what this X mark says what is to be done or what is going to be the current symbol available on the various tapes of the multi-tape Turing machine. So, the tracks are actually holding the input as well as the marker symbols. So, now how we are that is making these simulate that is behavior or how we are that is making a transition as far as this particular Turing machine is concerned. So, as far as the new tape is concerned, new Turing machine is concerned, that is N is concerned, it has to start from the left and visit all the k number of head markers from left and records all k symbols in its finite control. So, what will happen as far as this particular scenario is, you start from here, move towards the right until we find all the k number of that is X marks. The first one you record A2, and when you are looking at the second column there is no X mark, skip it, and when you are going for the third one from the current position we find an X mark is available. So, C5. So, if you are having storage on the finite control, A2 is going to be the one which is there in the first location of the storage and C5 is the information, or C5 is the symbol which is going to be there in the third position of the storage of the finite control. Then move towards the right. Now, we find an X on the that is your fifth of your that is third cell of the third track of fourth track of the Turing machine. So, we can record B5 into the second location of the finite control storage. So, we have read there is 3 number of locations because of 3 number of X marks have been detected. So, now we are having A2, B5 and C5 are the current symbols. So, we know what is to be done from the transition function. Now, it is going to be once again a move from right towards left. So, when you are moving from right towards left, you decide on what should happen for B5. If it is going to be a right operation, this B5 may be replaced by something like some D, and then decide on what should be the move, whether it is going to be a left move or it is going to be a right move. So, if it is going to be a left move, then you just remove the X from here and place it on B4. Similarly, when you are coming for C5, find out what is going to be replacement for C5. If it is something like E, and see whether it is going to be a right move or left move. If it is going to be a right move, you just move this X mark from this position towards the right. The same thing is going to happen even for A2. So, we need to traverse from right to left until we process the 3 number of X marks available in 3 different columns of the Turing machine. So, once it is done, then we can say that the Turing machine, there is one transition of the multi-tape Turing machine has been achieved. So, that is what here. So, when you are that is processing your N's head, that is the new Turing machine's head must visit all the k number of head markers from the left and record all k number of symbols in its finite control. Then N is finding the outputs. So, what should happen for the first tape and what should be for the second one and what should be on the third one. So, they are all actually that is done by revisiting each head marker on its tape and record the changes. So, it is going to be a move always from left to right until we find all the heads, and once again it is going to be a move from right to left until we find all the X marks from the that is your multi-track Turing machine. So, then we can say that it is possible to simulate or it is possible to do any operation which can be done with the help of a multiple tape Turing machine using a multi-track Turing machine also. So, then we can claim the language of the Turing machine is also going to be recursively enumerable, whether it is going to be a multi-track Turing machine or multi-tape Turing machine or it is going to be a single tape Turing machine. So, there is one more version of the Turing machine, we call it as non-deterministic version of the Turing machine. So, in all the previous cases we find that the Turing machine output is going to be unique, but it is not strictly required that the output of the Turing machine should always be unique. Even we can now, there is more number of outputs from the current configuration. So, there may be k number of distinct possible outputs, so that all the possible k number of moves may sometimes even be valid. So, even if you find or allow that more than one output is possible, then the behavior of the Turing machine becomes non-deterministic. So, we have NTM, that is non-deterministic Turing machine, which is whose transition function looks this. The current configuration, what it says is del of q comma x, which is going to be, normally it will be 1 only, q1, y1 and d1, where q1 is going to be the new state, y1 is a replacement given for x, and d1 is the direction in which we have to move. But now here we are having k number of outputs, q1, y1, d1, then q2, y2, d2, and finally it is going to be qk, yk and dk. So, you are free to select any one of the move from this particular that is output, it is not going to be 1. So, if you are finding that it cannot pick up a state from one and a tape symbol from the another one and the direction from yet another. So, always you select that is one pair, that is we are having one tuple, it is going to be q1, y1 or d1 or q2, y2 and d2. So, that is how the non-determinism available in Turing machines are defined. So, now the question is what will happen as far as the that is language recognition power of the Turing machine is concerned. Still the language recognition power is going to be same, whether it is going to be a non-deterministic Turing machine or deterministic or with multiple tapes and multiple tracks. So, the NTM accepts exactly same class of language as accepted by the deterministic Turing machine, and also because of the equivalence, for every Turing machine there exists an equivalent deterministic Turing machine also. So, how we are simulating that? So, we have the Turing machine that is Mn, that is nothing but a non-deterministic Turing machine, and the equivalent one is that is deterministic one, that is Md, but the condition is the language recognition power should be same. It means the language of the non-deterministic Turing machine is same as the language of the deterministic Turing machine. So, how we are simulating that? So, we are actually the MD will be designed as a multi-tape Turing machine, and the first tape contains the sequence of IDs of Mn which are completely separated by asterisks as seen here. So, this is going to be the IDs of the non-deterministic Turing machine. So, ID1, ID2 and ID3 etc., but they are all completely separated by asterisks. So, to say that one ID, a complete ID, then followed by an asterisk, then followed by another complete ID. So, this is what the tape content. So, now the first ID in general, it is going to be the one ID, or the first ID is going to be marked as the current one, and whose successor IDs are in the process of being discovered. So, we can't say that the entire the possible IDs are initially available in the tape. You generate the first one, the first ID, and from that, since it is going to be a non-deterministic Turing machine, there may be more than one possible output. So, we generate all the possible outputs, you do not miss even a single, and all of them will be simply copied onto the end of the tape. Suppose from this ID1, if there are 3 number of IDs possible, then store all the 3 possible IDs here. Then invariantly we must select the second ID. You see whether it is going to be the final ID or not, or accepting ID or not. If it is going to be the accepting ID, simply we can solve, that is declare that this string has been processed. If it is not going to be the accepting ID, once again from this ID you find out what are all the possible outcomes. Since it is going to be a non-deterministic Turing machine, there may be more than one possible output as far as this ID is concerned. Once again they all will be copied into the end of the tape. So, you are keep on that is generating the various possible IDs, and they all will be appended into the end of the Turing machine tape. So, every time when you are looking for a new ID, or when you are considering the current ID, you see whether it is going to be an accepting ID or not. If it is going to be an accepting ID, immediately we can say that the string has been accepted. So, it is the description here, where MD is examining the current ID and accepts if it is in the accepting state, and if it is not, you generate all possible new items, that is instantaneous descriptions from the current ID, and stores them into the tape 1 of the MD. that is a deterministic version. This is actually the tape of the deterministic Turing machine version whose IDs are currently generated from the non-deterministic version. So, we are appending them onto the end of the Turing machine, and MD is returning to the marked or current. After completely copying all the IDs onto the end of the tape, it will once again come back to the current ID, because current ID is always marked with some special symbol. So, to actually we will be selecting the current ID, then from there once again we will repeat the process. So, when the MD is going to accept, that is when the deterministic Turing machine is going to accept. So, whenever it enters into the accepting state, that is you can find that here, if ID 2 is the one generated as an output of ID 1, and when you take this ID 2 as the current ID, you check whether it is going to be an accepting ID or not. If it is going to be an accepting ID, then immediately we can accept, saying that this string has been processed. So, this is how we are that is dealing with the multiple number of non-deterministic Turing machine, and how we are simulating the behavior of a non-deterministic Turing machine with the help of deterministic Turing machine version. So, as far as the problem set is concerned, the proofs are very important, like how we are proving the multi-tape Turing machine is similar to the, or can be similar to the help of a single tape Turing machine. Even the non-deterministic Turing machine can be similar with the help of a deterministic Turing machine. And with the help of a multi-tape Turing machine, how do you construct a Turing machine, that is a stack operation. So, one stack will be, one tape will be used for holding the content of the stack, and the other one will be used for storing the input, the other one will be used for storing what kind of operation we are doing, and the other one can be used for storing the output from the stack. That is how we are simulating this stack with the help of a multiple tape Turing machine. And here is another string, that is your WW, and in the earlier case, if it is going to be WCW, which could be recognized without there is any kind of ambiguity or non-determinism, but whereas in the case of WW, the string is going to be an ambiguous, that is a non-deterministic string. So, it is required to find out only a non-deterministic Turing machine to recognize this string. It is not possible to develop a deterministic Turing machine for this directly. So, you come up with a non-deterministic Turing machine, and that can be translated into a deterministic Turing machine, saying that the recognition of WW can even be done with the help of a Turing machine whose language is going to be recursively enumerable language. These are all the possible questions as far as this particular topic is concerned. So, we have seen that as multi-tape Turing machine and its equivalent simulation, then the non-deterministic Turing machine, and how we are simulating the non-deterministic Turing machine with the help of a deterministic Turing machine. So, with this I conclude this episode. Thank you all.